So the question is, if we're trying to solve a problem related to amphachirality, which we had this exercise very early in the semester when we were first thinking about chirality in knots, to find an example of a knot diagram that has the same number of overcrossings as undercrossings, but which is a knot that's not amphichiral. So k is not the same as minus k. If we reverse the crossings, we actually don't get the same knot back. But here are the three knots with 6 crossings, 6-1, 6-2, 6-3. They're shown here in their alternating projections and totally reduced, so there's no Reitemeisters we can do to make them any simpler than these 6 crossings. And if you look at both the Conway notation, which is here, as well as the quantity in parentheses, this is a list of what are called the coefficients for the Alexander polynomial for these knots. One of them is not like the other, right? And it's 6-3. 6-3 has this wonderful symmetry that we notice, both in the coefficients of the Alexander polynomial on either side, 3 minus 2, 2 minus 1 as we go from the inside out, as well as symmetry in the Conway notation, 2, 1, 1, 2. Right? And so if we had this under our belt, we might expect that this of the 3 6-crossing knots is the one that's amphichiral, and the others are not. But it's worth thinking about why. Right? Why would we expect a symmetric Conway notation, because we don't know Alexander polynomials yet? Why would we expect that a symmetric Conway notation gives us an amphichiral knot? Or conversely, why would we expect that if the Conway notation is not symmetric, that that's somehow an indication that reversing the crossings is actually going to give us a different knot? So here's the Tangle 2, 1, 1, 2 that's represented. So in other words, these two are related in that there's a place I could cut on this knot, 2 places I could cut and then pin the ends such that this rational tangle is the one that, when we perform its numerator closure, gives us back the knot 6-3. And so if this is the tangle T, 2, 1, 1, 2, and I suppose I really want these extra brackets around there, but you know what I mean, right? Then what would be a name for the tangle that we would get if we just reversed all the crossings? So on the one hand, yeah, we would say that it's the same, except that now, for example, this 2 up here, which corresponds to this first 2 in my Conway notation, this 2, if I reverse the crossings, is going to turn into -2. And then this 1 down here is going to turn into a -1, -1, -2. So putting a minus in front of the tangle, reversing all the crossings, has the effect in the continued fraction representation of reversing the orientations of the crossings that build up our tangle. And if we want to know whether these two things are the same, what tool do we have for judging whether 2 tangles are in fact isotopic? Let's build the continued fraction with these coefficients and just see what we get, right? So for 2, 1, 1, 2, I'm going to actually ask you to do this real quick, because this could give you that important sort of evidence that you could use on the first homework problem. Take a moment and compute each of these fractions and see what it is that you get. Well, what's notable about this, first of all, is that even in weird continued fraction land, it seems that reversing every one of these coefficients just ends up reversing the value of the tangle. But try it with one of these other ones. Try it with 4-2, maybe, as an example, and see if you get.
Yeah, because we want to
right. So compare 4-2 to -4, -2, and see if that same result holds. So reversing all the coefficients in a continued fraction is always just going to end up reversing the fraction. So maybe the question that we need to be asking is, what knot operation corresponds to the reversal of order in a continued fraction? Like, what if I took and I made the thing 2-4 instead of 4-2? What would be the relationship of that?
And aren't we assuming that -4, -2 is actually a simplified knot?
A -4, -2 is actually a simplified knot. Well, that's a good question. How do we know? If 4-2 is the Conway notation for this knot, then do we know that -4, -2 is that's going to be a Conway notation for the inverse, the mirror of this knot, right? Whether it's simplified, I think we can make the argument that it is still simplified. Right? Reversing all the crossings in a projection for a knot is not going to change whether or not that knot projection is reduced or not.
Because we didn't reflect it yet.
Because so what's the Tangle 2-4 going to look like compared to the Tangle which built this, which was 4-2? It's just going to reverse the roles of the vertical twists and the horizontal twists, so that what I'll get is something like this. 1, 2, 3, 4, and then after that I'll have 2. And then I'll take the numerator closure of that. Except that that's actually the same knot that I just have here. So I think I have that sideways. So what I wanted instead was 2 twists this way, followed by 4 going this way. Come around this way. Oh, whoops, what did I mess up there? So there are my 2 twists. Yeah, yep, that's what I wanted. And then we take the numerator closure of that. So actually something interesting happens when I reverse the Conway notation. This thing actually isn't even a knot anymore. So
yeah, 'cause that would be a link.
yeah, 2-4 is not even a knot. So there's something more subtle going on here than we're giving credit for. We have one component there in green and the other component here in purple. And this purple component is not a very interesting one. If you notice, we can untwist almost all of it, and we end up with something which is just isotopic to this. How do I draw this? This thing that we call the hop link. It's just, that's all it is. So something really drastic happens when we reverse that Conway notation. Whereas if we reverse the Conway notation for this one, we clearly get back the same, not only a knot, we get back the same knot if we just write it backwards. So something about the palindromicity of the Conway notation is telling us something, but it doesn't seem like it's quite specific enough just yet. But it certainly does seem to be a clue.